Uh, yeah, so welcome back. So, the point where we ended the last class is uh, basically where I mentioned that I want to show you some examples of fluid flows, which I think is great fun and cool and non-intuitive and so on and so forth. Uh, yeah, so I'll just show you some videos. I'm not an experimentalist, but figured out some YouTube videos, which I hope you will enjoy and get interested in knowing more about fluid mechanics. In some cases, I will talk and give a brief overview of what is happening. In other cases, it's explained so well uh, that I will just not give a voiceover because that will be more of a disturbance. And basically, I'll be talking over different instabilities, right? Uh, Initially in Newtonian flows, and in some cases over non-Newtonian flows. So, without much ado, let's jump straight ahead. And so, this is all our YouTube videos, and here is the so-called Rayleigh-Plateau instability, and it basically explains uh, or analysis of the fluid dynamics equations basically explains why when you suppose have a streamlined flow from a tap, suppose you open it slightly and keep on decreasing the flow of water from your tap, uh, and if you keep on decreasing it beyond a certain point, there will be a stream of water and it will break up into small droplets, as you can see here,
Of droplets is most consistent.
right? Now, the reason, yeah, so the reason it breaks down into droplets is basically the surface tension effects. If there's a certain there's a certain perturbation on the surface of the fluid, there's a pressure difference created due to surface tension, and the water flows um, into the less from the high pressure to the low pressure region so that it forms droplets, and that decreases the surface tension. You know, the spherical objects have the least surface area, and thereby it decreases surface tension energy. Now, that part is understood, and some part of the analysis understood, but I will try to show you. Yes, let me see. So, if you see carefully, with each droplet, there is an additional smaller droplet. So there's one big droplet, a small droplet, a big droplet, and a small droplet. I don't know the reasons for it. So here you see again big droplet, small droplet, big droplet, small droplet. Now, why there should be a sequence of big or small droplets, I don't know. But I once heard about it in a conference and I thought, oh, it was pretty cool. This simple uh, breaking up into all same size droplets, and moreover having a big droplet, small droplet, and so on and so forth. But anyway, this can be understood as the Rayleigh-Plateau instability, and one can figure out the length and analyze the length of after which it will break into droplets, and so on and so forth. You can do a search here. You can, I think, see the bigger and the smaller droplets better. Big droplet, small droplet, big droplet, small droplet. I don't know the full physics of it. I mean, by a small droplet. But anyway, I thought this was pretty cool and nice. Now, here, this video is so nice. I think there's no point in me speaking. So, this is so called Marangoni bursting. So this is again a surface tension effect, and the French groups are extremely strong in fluid mechanics. So I'll just let you watch the video and not even fast forward it. I hope the sound is also getting recorded, and but you can read. So this is basically a drop of water on. Here again, you see there were two droplets, one big, one small. Yeah, well, I would consider this to be too beautiful. Uh, then, furthermore, Kelvin Helmholtz instability. Just one second. So, Kelvin Helmholtz instability, in this case, essentially what you have is fluid of lower density, say air, on the sea surface, water, on some other fluid which is of a higher density, and there are the two are flowing in suppose opposite directions, or at least they're flowing in with different speeds, suppose, okay, with relative to the other. So then there can be a height fluctuation, and when there's a height fluctuation, basically this part is then pushed, and some pressure difference and so on and so forth. Bernoulli lines, I'm not going into the detailed physics, is pushed, and what you see is the Kelvin holds instability, and uh, let me see here, the entire physics is described, but I think there is some. If I remember, there were some. Yeah. So you see, as a consequence, wave-like patterns forming even in the clouds, right? Uh, so here, so this is an example. So waves forming, so waves formed due to Helmholtz instability, and you can also see it up there in the clouds, and somewhere else from, there's a picture taken from just one second. So some pictures from the some spacecraft. But meanwhile, I have to ensure that my recording continues. Stay in the call. Okay, and it can also be seen in the lab. This is by my friend from ID Kharagpur. He's in Chirag Kalilkar, and he set up this experiment in the lab to see Kelvin Hall's instability. And here you see two liquids, the higher density liquid on the bottom, lower density liquid on the top, and this interface is being maintained. And to fill up these two liquids in this glass chamber, uh, while maintaining the so that these two fluids don't mix, was apparently the biggest challenge for doing this experiment. But let's see. Can you see Helmholtz instability? He slightly turns it. The liquid is flowing with respect to each other, and you see the swirls. It very quickly starts mixing up here. So anyway, so that's Kelvin Helmholtz instability, fresh water over dyed brine by Chirag. Okay. Some other stuff. So suppose you have two plates. You have a fluid between two plates, so that the top is at is lower temperature and the bottom is at a higher temperature. There are, of course, beyond a certain point, convection currents which are set in, uh, but they become swirls like this. So this is from a computational fluid dynamics CFD, computational fluid dynamics video, which has showing the Rayleigh-Benard convection swirls. But you can also see it in the lab. And I think here I will again stop my voiceover. And what is happening here is this person is taking some fluid, put in some mica particles so that you can visualize the fluid flows, right? Uh,
This means literally current show. This will allow us to see oil. As the oil heats, we can see a pattern formed in the mica powder. This pattern is Bernard cells caused by Rayleigh-Benard convection. As the oil at the bottom it becomes less dense and thus begins to flow to the surface. Once it reaches the surface, it begins to spread out because the surface tension of warm oil is less than that of cool oil. Cool oil begins to pull together at the edges of the Bernard cells, pulling the warm oil away from the center. Once the oil has reached the edge, it begins to cool and sink down to the bottom of the dish where it can be reheated, forming a feedback loop. Once the cells form, they are very stable provided the temperature doesn't drastically change. Taking a look with the infrared camera, we can see this temperature gradient across the Bernard cells. At the center of each cell, it is much warmer than the edges, forming this dark grid across the surface of the oil. Whether or not the Bernard cells form is determined by a non-dimensional parameter called the Rayleigh number. The Rayleigh number is the acceleration due to gravity.
so we'll come to all of this, the various dimensionless numbers, which we shall introduce to you, hopefully, before I go on and start discussing each of the equations term by term. So this was all examples of Newtonian flows, Newtonian fluids. With non-Newtonian fluids, you can have even more fun. Okay, so let's start with this. So this is a fluid, but it's not a normal fluid. It's a polymeric fluid with a very high molecular weight. And well, you know what happens when you pour water out like this, right? I mean, this is hardly anything, but not, hardly surprising for you. But now, if you take some whatever this polyethylene glycol, whatever be it, some polymeric soft matter solution, and when you pour it, let's see what happens. I think so. I'll fast forward it a bit. So this is viscoelastic fluid. There is elasticity involved as well. So this is a viscoelastic fluid with elasticity involved as well. So yeah, so this is a non-Newtonian fluid flow, right? And this is a Weisenberg effect, but I'll show it in another video. Uh, so this is G.I. Taylor. You'll come across the name Taylor, Quet instability, G.I. Taylor all over fluid mechanics. And this is an extremely famous video. No, it has now become famous, where you will see, let me know. So what he does is he does exactly this. He puts, okay. Now what he does is rotate the fluid, and it's a highly viscous fluid. Oh, okay. And this is not the video I wanted to show you, but never mind. There is one more. Yeah, yeah. Okay. So here the fluid apparently mixes, but for highly viscous flows, V dot grad V term in the Navier-Stokes equation doesn't become, doesn't contribute this low Reynolds number flow, and you get basically uh, time reversible equations of motion. I'll at the end I'll show you a better video maybe if I can find. So here there is some other fluid made of maize, and it flows as you see. But when he holds the fluid in his hand, and as long as he shall keep applying stress to it, it starts behaving like a solid, because you can't hold a liquid in your hands. So here what happens is you are seeing the phenomena of shear thickening, as a consequence of which you have essentially uh, yeah, so this is behaving like a solid, but as soon as he stops applying stress to the flow, you will see that the fluid will start flowing. Yeah, so that's the phenomena of shear thickening. And again, it's a non-Newtonian fluid, right? Now I'll show you the phenomena of shear banding. So what you will see here is basically you have this liquid and these speckles. So this is a polymeric liquid. These speckles are just for the sake of visualization. And when you will, they will shear the fluid. You'll see that you will initially have a uniform velocity gradient which will form, but then it will break up into two layers, one of which moves fast and one of which moves slower, or it has a two different strain rates. I think that is the better way to. So now you see it's moving but now it is broken up into two parts, and this part has a higher strain rate as compared to the flow here. So this is the phenomena of so-called shear banding in fluids. I don't know. I have intentions to work on this. I have a model which has shear banding. So this is the phenomena of shear banding, and then you can see the meandering thread experiment. And I was lucky enough to see it in my own with my own eyes in University of Toronto. So here, what was being done what is being done is basically there is a plate which is being moved at a constant velocity, and honey is flowing at a constant rate. This was done by Stephen Morris and University of Toronto. And if you would have seen that initially it was moving in a straight line, all that this person is doing is not change the rate of flow, but change the speed of this flow of the plate, as a consequence of which you start getting these meandering flows. uh, okay, so it starts to meander the way you see, and he keeps on decreasing it, and you can see the consequences. He keeps on decreasing the velocity of this motion of this yellow plate, and you can yourself see what are the consequences. In the last decade, after he had done these experiments, the reason for such things was not known, and he has a couple of PREs and at least two or three papers trying to understand the origin of these various I don't know, instabilities. So the nature of the flow is changing, right? So this is called the honey meandering experiments. Again, it's a consequence of viscoelastic flows. You see, this is moving at an extremely slow rate. Stephen Morris, University of Toronto, right? uh, the so-called Weisenberg effect. So here you have taken a non-Newtonian fluid and you are rotating it, and you see that the fluid is climbing up this rotating uh, rod, right? And this is what is happening is there's a polymer solution which is being stretched, as a consequence of which, so on rotating, the liquid begins to slowly climb the rod in an effect known as the Weisenberg effect. Many non-Newtonian fluids exhibit the Weisenberg effect, and when they get stretched due to the rotational motion, there's a pressure which is created towards the center, towards the rod, as a consequence of which the liquid starts, right? So this one is showing, yeah, I don't think. I think this is pretty cool and funny, if you like, right? Here is some other non-Newtonian fluid which is being vibrated on what is this called, a speaker. And you can see how the non-Newtonian fluid behaves. Of course, you won't see this in a for a Newtonian fluid. So here, non-Newtonian fluid in a speaker cone. Of course, he has to sacrifice, I guess, his speaker. Uh, yeah, so I think you have already seen. By the way, these movies are there. Some of these movies are also there in my research page, and here you have fun YouTube videos on soft matter properties. So you have all of these. You can see it later if you like, and some other articles as well, and so on and so forth. Uh, so last, I'll try to see whether I can show you that video with three color droplets. It's called, never mind, I'll add it somewhere. So I'll stop recording right now.